Hello everyone, welcome to this session where we will explore an exciting concept on GPU programming, matrix addition using unified memory in CUDA. In this video, we will break down the steps of implementing matrix addition, highlight key concepts like unified memory, and analyze performance differences between the CPU and the GPU. Unified memory is a memory management technique that allows both the CPU and GPU to share the same memory space. This eliminates the need for explicit memory copying between host and the device, making programming simpler and more efficient. It is particularly useful for applications requiring frequent data exchange between CPU and GPU as it reduces programming complexity and overhead. The hardware and the software requirements are uh, an NVIDIA GPU enabled system, CUDA toolkit, NVCC compiler, Google Colab, or a similar environment for implementation. The step-by-step explanation of matrix addition implementations. First, we have to initialize the code by we start by setting up the CUDA device and initialize its properties to determine the GPU's capabilities. Memory allocation. Next, we use CUDA malloc manager to allocate unified memory for matrices A, B, and C. This ensures a seamless data access between the host and device. Matrix initialization. We initialize matrices A and B with random floating point values using a helper function called the initial data. Host computation. To verify the GPU results later, we compute the matrix sum on the host using a simple used nested loop. Kernel launch. We define the grid and block dimensions for the kernel launch. Each thread computes one element of the resultant matrix, where the kernel functions can be found before the starting of the main function. Synchronization and timing. The GPU computation is timed using CUDA device synchronize and the results are compared to the host computation for correctness. Cleanup. Finally, we free the allocated memory using CUDA free and reset devices. This is the program for the with the memset where the output can be given and the output has been taken. And the next one is without a memset where we use this program so the output can be taken here. Yes. Performance analysis. We measure execution time for on both the host and the GPU. As expected, the GPU performed significantly faster due to the parallel computation impact of memset. When a memset was removed, we observed slight variation in initialization times, but the overall performance impact was negligible during kernel execution. Challenges and observations. Unified memory advantages. Unified memory simplifies memory management, but it might introduce slight overhead due to implicit data transfers. Potential bottlenecks. Ensure proper grid and block dimensions to avoid under utilizing the GPU resources. Conclusion. Matrix addition using unified memory is a fundamental example that demonstrates the power of CUDA for parallel programming. This approach simplifies development while providing significant performance improvements for large datasets. The GitHub repository link has been given and the result will be provided in the below description, where in the GitHub we can view the output of the program with memset and without memset clearly on the GitHub repository link which will be given over. Uh, If you are new to Keyboard programming, I encourage you to try this experiment. Explore more advanced topics like matrix multiplication, optimization techniques, and memory profiling using tools like NVProf.